Hi class, welcome back to Electromagnetics. So today we want to continue our analysis of transmission lines. We've already looked at transmission lines from some different aspects in the frequency domain. Now we want to extend that to the time domain. So we're going to look at a few aspects that involve that. First, a quick historical background. This person was educated at Boydoin, I guess how you pronounce that, college, and then Johns Hopkins University. He worked at Harvard. This is a photograph of this individual. And this is Edwin Herbert Hall, lived from 1855 to 1938. So some notable things of Mr. Hall. He did extensive research in relations to the relationship between simple resistance and magnetic fields. So of course that contributed to our study, electromagnetics. One result that he discovered was the Hall effect. And so the Hall effect is used extensively today in magnetic sensors. And it has to do with separating of the flow of charged particles. There's some videos on YouTube that I think handle that pretty well. Maybe I'll put one on the page site. If not, you can go find it. And this led to, again, the understanding that current flows from negative to positive. Up to that point in time, they were unsure and they assumed positive to negative, but his test proved conclusively that it flows from negative to positive. So again, we're going to continue in part 7 of the course, transmission line analysis. And like I said, we've covered frequency domain. Now we're looking at some aspects in the time domain that should be of interest. So let's go back and look at a simple circuit here. Just a simple circuit where you're terminating in a resistor. So in this case, this should be similar in many ways to what you've seen in some of your circuit analysis classes. We'll have a voltage, and then we have some load resistor out here. Now this is going to differ a little bit, at least the way we look at it, as we're going to have some impedance. It's not a perfect source, so it'll have some impedance here. But instead of just saying these are conductors, now we're saying it's a transmission line. And so this is really the case all the time. But when it comes into play and when we really have to take this into account is when we get into higher frequencies and higher switching times. And so the things we're going to talk about here, when you're doing your regular circuit analysis like Ohm's law and Kirchhoff's analysis and stuff like that, you don't have to worry about this because we're assuming that everything is already in steady state. So that's the important part. Here, we're trying to see what happens before that steady state, because even in today's technology, as devices function faster and faster and we switch faster and faster, some of the things we're going to look at today come into play, and they can actually make circuits behave differently than what you think they might if you don't take everything into account and analyze everything properly. So some of you that might go into microchip design or electronics, very high-speed electronics, some of this will be of use to you as you move on. So let's think about this. At the instant the switch closes, the source sees an equivalent circuit as below. So notice that at this point the source doesn't see the load resistant yet. It doesn't know what's out there. So this is a major difference, as I was talking about in the last slide, between lumped circuit theory and transmission line theory. So what you've learned up to now is lumped circuit theory, and that's where we're assuming you get to steady state pretty quickly, relative to whatever you're trying to do with the circuit. So in transmission line theory, that's not always the case. So that's what I was saying. So we have to look at it a little differently. It's the same circuit, but we're analyzing it a little different way. So when that switch is closed, what it sees then is, instead of the load resistor here, we see the characteristic impedance of our transmission line, right? So this is what the source actually sees. And so that was what we used to calculate this RG and this Z0, our initial current on the line. So at this point then, the circuit is just a voltage divider, just like I said, and so we can describe this mathematically pretty easily as the source voltage times the intrinsic impedance over the sum of the intrinsic impedance and the impedance of the source. Likewise, so we'll say V plus, because this is what we'll say is our initial condition on our transmission line, transmitting. If we put a minus sign up here, that means reflecting. So we also can calculate our current. So your current is just your voltage over your impedance, Z naught. And so when we do that, of course, the Z naught divides out. So this is our initial current on the line, this I plus. So the traveling wave then on our transmission line will reach the load at a time L over the phase velocity. So whatever the phase velocity is, and that's going to be determined by what your dielectric material, if there is any in here, might be. And so at this point in time, that's when we approach Z equal L, where we see our load resistor for the first time. And so when this happens, now we have a boundary condition, right? Because we're assuming that this load resistor is not matched with our transition line. So we've seen from Maxwell's equations that this will cause some reflection. So that's why you're starting to see the notation here now. We have the V plus, which was our wave that was originally transmitted, but now we also have on the line this reflected wave. And we're saying in terms of voltage, but remember we've shown clearly that on a well-defined transmission line, that's really a representation of your E field or your electric field. So voltage and electric field are pretty much synonymous in this case. All right, so again, that produces this reflected wave. And we can calculate the reflective wave, again, by using this ratio. And so this V minus is going to be equal to our V plus, or voltage reflected is equal to our voltage originally transmitted. And that's RL minus Z naught over RL plus Z naught. Again, this is simple circuit analysis. So now we can define a voltage reflection coefficient at this point. And so, as we've seen in the last couple of slides, that's just going to be RL minus Z naught over RL plus Z naught. And likewise, we can determine the current, electrical current reflection coefficient, which is just the negative of the voltage reflection coefficient. So now the reflected wave then travels back the other direction, and that's going to take 2 times this. One go all the way in the forward direction. It's L, our length, over our phase velocity. So when we do that time, hit that time again, our reflected wave now has come back and arrived at our original points where we've connected our source. So now this reflected wave sees the source resistor, and because of this, guess what? We have another boundary condition here. So we've got our original conducting current, we've got our and voltage, we've got our reflected current and voltage, but now we have our re-reflected. So you see we now have this V minus plus. That means this is the part of the wave that's going to be transmitting as a result of the reflected wave coming back, reflecting again. So it's kind of a bouncing condition we start to see here. So at this place where we have again a boundary condition, we can calculate what this new voltage V minus plus is as a ratio of our resistors and impedance. And just as we did before, we can calculate another reflection coefficient. So this will be our reflection coefficient at the source. And again, the current's going to be the negative of that. Okay, so now we have 2 boundaries in this circuit, simple circuit, 2 boundary conditions, 2 reflection coefficients defined. So as you can imagine, once again, this re-reflected wave, V minus plus, will travel down the line, and after 3 times our time constant, which is 3L over phase velocity, guess what? This re-reflected wave sees the load resistor again, and again produces another re-reflected wave defined back towards the source again. So this process, as you can imagine, it's not hard to visualize, I don't think, will repeat indefinitely, depending on the values of the voltage of the waves and the reflection coefficient. So this will keep going back and forth until, again, we reach this steady state condition. Now, the steady state condition is where we are used to arriving on the scene in our lump sum lumped circuit analysis we learned back in circuits class, sophomore, junior year. So this process can be tracked then using a bounce diagram. You might also hear it referred to as a reflection diagram, or you may hear it referred to as a space-time diagram. So these can be fairly useful. So we want to demonstrate the bounce diagram with the following example. So let's see how this works. So we're going to consider the same scenarios we had before, but let's put some values in there. You can see that we have a transmission line that has an intrinsic impedance of 60 ohms. We have a 100 volt source. We have a 40 ohm impedance that's associated with our source. And we have this load out here that's 120 ohms. Nothing's matched. And we're out some distance L. And we're going to close this switch at t equal to 0. Okay, so we can go ahead and calculate what our initial transmission voltage is on the line. So that's going to be our 100 times 60 over 40 plus 60, just as we saw before, and so that gives me 60 volts. And then our current, we just divide that out, and so we have 60 volts over 60 ohms, the impedance here, and so that gives us 1 amp. So that's our initial amperage on there. We can also go ahead and calculate our reflection coefficients. So over here at the load, we're going to have 120 minus 60 over 120 plus 60. So this reflection coefficient over here is 1/3. And then back at the source, which we'll call tau with the S subscript, the L subscripts for load, S subscript, it's going to be 40 minus 60 divided by 40 plus 60, so that gives us a negative 1/5. So we have negative 1/5 on this side at this boundary condition. So should have everything we need now to start analyzing what's going on. We have our initial conditions, we have our reflection coefficients, we have our time that it takes to propagate, so let's take a look and see what happens. So here's our bounce diagram. Let's think about how this works. So as we're moving down the diagram, you can see we go 0, 1, 2, 3. So this is our time in microseconds. We said it took 1 microsecond to travel the length of our transmission line. Okay, so we start out here at time 0. When we close the switch, we calculated we'd have 60 volts. So this 60 volts is going to travel down the line until we get to 1 microsecond. So at 1 microsecond, we hit the load here. Okay, so up until that time, there's 0 voltage seen at the load. So now, because of our reflection coefficient, we take 60 times 1/3, that gives us 20. So that's going to send a wave back towards our source of 20 volts. So we've got 60 volts, that's the standing wave coming from the source. We've got that's transmitted. We've got the 20 volts that's reflected back. So the voltage that we'll see at our terminals until something else happens, which will be in another 2 microseconds, the time it takes for this wave to go down and back, we could actually measure 80 volts at our load, 80 volts. Okay, so again, we have another microseconds going by, this 20 volts is going down, then bang, at 2 microseconds, it reaches our source. So at this point, we have the reflection coefficient negative 1/5. So negative 1/5 times 20 is negative 4. Okay, so now the voltage on at the terminals where our source is going to be the addition of all of these. So we'll have 60 plus 20. 60 is the transmitted wave, 20 is the first reflected wave, and minus 4 is the second re-reflected wave, minus 4. So 60 plus 20 minus 4 is 76. So now from 2 to 4 microseconds, if you were able to measure that voltage on those terminals, you would measure 76 volts. And so now again, it takes another microsecond for this negative 4 volts to go down till bang 3. So at 3, we apply our reflection coefficient again. So the negative 4 times 1/3 is negative 4/3. So we send that back reflected again towards our source. And now our voltage on our terminals will be 80 minus 4 minus 4/3, which if you do the math, that comes out to be 224/3 for your voltage that you'd measure there. Again, this negative 4/3 takes a microsecond. When it hits, we multiply that times negative 1/5, so that sends 4/5 back up. So now if we say 76 minus 4/3 plus 4/15 be 1124 over 15 volts, if you were to measure there. And you can see this goes back and forth, just continuing in the same manner. Same thing with the current. So we have that 1 amp going down at 1 microsecond. We multiply times negative 1/3. And so the current that we would measure if we had an ammeter at the source would be 1 minus 1/3 would be 2/3 amp flow. And here we're seeing 1 amps until this reflected current comes back. And so we reflect it again times 1/5. And so that'll be negative 1/15. So now we have 1 minus 1/3 minus 1/15 should be 9/15. So again, as every microsecond passes, we start to see this bouncing going back and forth and this accumulation. So this is important for a couple of reasons. If you think about it, if you're dealing with logic gates like AND gates and OR gates or something like that, and you start to switch these things really fast, and you have other inputs that will be contributing, you may have something that only happens like every 8 microseconds or 10 microseconds or even milliseconds. If you're in the milliseconds, you're fine. This thing will reach steady state without a problem. But if you get up to really fast switching times in microseconds, you could hit in the middle of this somewhere. So like after 2 microseconds, you may not be sure if you have a 1 or a 0 or what's going on, or it may not be enough to hit the threshold of your logic gate. So that's where this kind of comes into play. So if you have some logic that's not maybe functioning the way you think, or it's not consistent or repeatable, you may need to look at your switching times and what's going on here, and you might need to adjust your clock speed to give this time to ring out or reach a steady state. Of course, the steady state equivalent circuit we can calculate again from just our lumped circuit analysis, and when we would do that, we should be able to tell pretty quickly just from Ohm's law our voltage across this resistor would move towards 75 volts, and our steady state current would be 0.625 amps. And if you were to continue down those bounce diagrams on each side and continue to add things up and go down, you'd see it would incrementally approach these two numbers, and that would be our steady state numbers. So, if we were to take a snapshot of what's happening on our line, so here's our line, here's where our source is, here's where our load is, and this is halfway in between. If we were to close the switch and then at 2.5 microseconds, so that's kind of halfway between our third step, this is what we would measure all the way across the line at every point on the line. So remember, after 2.5, the 60 volts has come down and it's reflected back. So we've got the 60 plus the 20, so it's the 80, you'd see 80 volts all the way down to L over 2. Now from the source, we've sent the 60, we've received the 20 back, and we've sent the minus 4 back again, and it's halfway down the line. So you would measure 76 volts all the way up to L over 2. So same thing with the current at T equal 1 1/3 microseconds. You can see that the 1 amp came all the way down, and then 1/3 of a trip back. We have to subtract that or add the negative 1/3 reflected back, and so you'll see an amp flowing all the way if you could measure it on your line up to this point. But then from the load back to this point, you would only measure 2/3. And again, it would keep adjusting, maybe going up and down until it finally hits the steady state of 0.625. So we can also monitor the voltage and current at points. So we could say at Z equals 0, we want to track what's going on. So again, we see here it's 60 volts until we hit that 2 microsecond point. That's when we've had time for the reflected wave to come back. And then at that point, it jumps up to 76. And then 2 microseconds later, it dropped down to 1124 over 15. And then after 6 microseconds, it goes up. So you can see it's starting to approach our steady state level. And so we will get there eventually to the 75 volts, but it gets there incrementally. This is the way things really happen. If you're looking at really short times after the moment you close the switch. Again, you can also look here at the load. So at the load, we don't see anything until 1 microsecond, jumps up to 80, volts, and drops down to 224 over 3 volts, then goes up to 3376 over 45 volts, so on and so forth, and it's approaching that 75 volt level there. And so as well, you could pick a point halfway between. So at half a microsecond, it jumps up to 60, and then a microsecond, after 1 microsecond, it jumps up to 80, then back to 76, and you can do the same thing with the current. So you might want to just take some time and see if that makes sense, looking at those previous bounce diagrams and these diagrams to see if you can see what's happening at different points in the line. So it's worth noting that the steady state condition of the overall circuits, it's actually a combination of all the steady state conditions. So it's all these waves and reflected waves added together. So we can see that here. So our voltage is at the source 60 minus 4 plus 4/15, so on and so forth. And what this really is 60 times 1 minus 1 over 15 plus 1 over 15 squared, so on and so forth until we get to 56.25 volts. Again, our current steady state, 1 minus 1 over 15 plus 1 over 225, same thing, 0.9375. And then this is the steady state transmitted. This is the steady state reflected. So you'll have your 20 volts minus 4 over 3 plus 4 over 45, so on and so forth. So our total reflected steady state is 18.75. And then finally, our steady state current is reflected, again the minus signs, negative 1/3 plus 1 over 45, so on and so forth, until we get to this minus 0.3125. And so to get to the steady state that we would measure there for the voltage, it's going to be these two added together, the transmitted and reflected wave, they would add together to give us our 75 volts. And then for our current, if you take 0.9375 and subtract 0.3125, that should give us our 0.625 number. So one last example, let's consider the same scenario as before, but with the exception that the source now produces a pulse that extends from 0 to 1 microseconds. So to understand this, we need to redraw the bounce diagram as before and modify it by applying superposition principles. So here's what this looks like. So here, same thing as we had before, but now we close, and so we have 60 volts from 0 to 1, but from 1 to 2, our source is off, right? So we don't have any contribution there. And so this pulse will travel down until it gets to this point. So at this point, it's much like it was before. We have our 60 volt, and then we reflect 20 back. Okay, but that only goes for 1 microsecond. You can see we go back to 0 after that. And so this travels down, and now at this point, we have our 20, and then our reflected of minus 4. And then again, going back this direction, we'll have our minus 4, and then our minus 4/3. So it's similar as before, but we have this gap in what's going on. And this can really wreak havoc if you're dealing with switch logic gates, trying to keep up with all of that. So as before, we can now plot the voltage versus time at key locations and look at the reflected, how the transmitted and reflected voltages interact. So at 0, you can see we would see 60 volts into 1 microsecond, and then we would see 16 volts from 2 to 3 microseconds, and then negative 16 to 15. That's because our source isn't continuing to contribute. Same thing here at the load. You'll see from 0 to 1, we don't see anything, and we still see that 80 that we saw before, and then nothing from 2 to 3, and then from 3 to 4 microseconds, we would see the negative 16 over 3, and so forth. And then our voltage in the middle, which is kind of interesting, it doesn't have these gaps because we're always passing, the transmitted and reflected waves are passing each other. So we'll see the 60, and we'll see the 20 coming back, the negative 4, so on and so forth. So this is where, as you can see, if I were to send 1 bit and then turn it off, you're going to see some ringing here, which could confuse the logic gate, and depending on what it's contributing to and switching, could cause more problems. So something to think about there. So now we can use these waveforms to apply superposition to see how the voltages vary with Z at a time t equal 2.25 microseconds. So if we were to take those graphs from before, we would see that our voltage at 2.25 microseconds on our line would be 16 up until a quarter of the way down the line, then it would be 20 from a quarter to 3/4 down the line, and then from 3/4 to L would be 0. And again, this is a result of these two added together. I guess I should have said that. So this is my reflection from the original transmission. This is my original reflection. So you can see 20 minus 4 gives me 16. 20 plus 0 is 20. 0 plus 0 is 0. So just things, again, might want us to go back over this and look at it and think about it, of how this works now that we're taking into account transmission lines and incredibly short times after we have a change in the condition on our circuit and before we reach steady state.